Okay, in this activity, a company claims that the standard deviation of the length of time it takes an incoming telephone call to be transferred to the correct office is less than 1.4 minutes. A random sample of 25 incoming telephone calls has a standard deviation of 1.1 minutes. At an alpha of 0.10, is there enough evidence to support the company's claim? A couple things I want to point out here before we go forward is that I've circled standard deviation. Our previous problem, they gave us variance. I'm circling this because I want you to be aware of some things that we need to be aware of as we move through this. They gave us standard deviation, and we're going to have different points where we have to deal with variation. Okay, the other thing is that because they gave us standard deviation, our measure of 1.4 minutes, we have this unit measure. It's not minutes or not seconds or hours, but minutes, where we didn't have a unit measure when it came to variance. Okay, moving forward. Looking at this, you're thinking, well, yeah, they claim that it's less than 1.4 to route an incoming call, and our sample came up with a standard deviation of 1.1. Well, what we want to know is, can we safely say with 90% confidence that 90% of the time when calls come in, they're going to get routed in less than 1.41 minutes? Can we be certain of that? Is it enough of a difference that we can say that that's going to be 90% confident? So that's what we're testing here. So our null and our alternative are as before. Our standard deviation, the population standard deviation, is equal to 1.4. The alternative is that it is less than 1.4. Now I'm also including here that, the variance is standard deviation squared. So if I squared each of these, this 1.4, I would have a population variance of 1.96. So I've done that in each of these cases. So I'm just pointing out that the claim is here in our alternative, that they're claiming the standard deviation is less than 1.4, therefore the variance would be less than 1.96. That's where our claim is. Okay, our confidence level is 90%, our alpha is 0.10. This is the left tail test because they're saying it's less than. We're wanting to look for the critical value that has 10% in the left tail. So we have a sample size of 25. That means we have degrees of freedom of 24. Our critical value would be 15.659. That, I want to show you where I found that. When I'm looking at my chi-squared table, my chi-squared 0.9, this column right here, now that is reflecting 90% to the right. That means I would have 10% to the left, and that's what I need. So I'm going to go down to my row of 24 to get the 15.659. So that's how I got that value. Back to this. When we go to plug in our test statistic formula, we have the degrees of freedom times our sample variance divided by our population variance. That's where I needed those standard deviations, both of them squared. So I'm just pointing that out, that our sample standard deviation was 1.1, and I need to square it here. Our population standard deviation that we're testing is 1.4, and I need to square it here. In our previous example, we were given our variances, and I didn't have to square anything because they were already squared. Here, when you are given standard deviation, you need to plug them in and square them, because in this formula, you need variance. So I come up with a test statistic of 14.816, which is a little less than 15.659. When I draw the critical curve, we can see that falls in the rejection zone because 14.816 is less than 15.659, so it looks like we're going to be rejecting. In order to do the p-value and the confidence intervals, I'm going to need to go to StatCrunch. I need to get rid of this. I'm going to go to, sorry, I need to put that in the middle for us. I'm going to go to Stats, down to Variance Statistics, down one sample, and then down to with Summary. Okay, so this is something I need you to be aware of. StatCrunch is going to ask for sample variance. Our problem gave us standard deviation. So our random sample of 25 incoming calls has a standard deviation of 1.1. I need to square that because I need sample variance, not sample standard deviation. So 1.1 squared is 1.21. Our sample size was 25. Okay, when I go to do my hypothesis testing, My population variance that I am testing is 1.96, not the population or standard deviation, which is what they gave us. So I need to plug the 1.96 in here. And go ahead and compute. Oops. Something in here wrong. Oh, I need to change the sign to less than. There we get our test statistic of 14.816 and our p-value of 0.074. Now, in order to do the confidence interval, I'm going to go back here to options and click edit. I leave the variance, I leave the sample size, I need to come down here to confidence interval. Now remember, our problem was leaving 0.10, in other words 0.10 alpha, 10% in the left tail. And so the confidence interval that has 10% in the left tail would be the 0.80, because that would have 10% in each tail. A confidence interval is a two-tailed event, and so we need to have a confidence interval that has 10% in the left tail, and that would be 0.8. So when I click compute, I get a lower limit of 0.875 when I round that, and an upper limit of 1.855. And we really can't compare that very well. I'm going to close that down. I don't need that anymore. I can't compare that very well because the information that was given to us was standard deviation. So I want to take both of those, because that's variance. I want to take both of those and square root them to get a standard deviation of 0.93 and for the lower limit, and an upper limit of 1.36. Now the 1.4 population standard deviation that we were given is outside of that confidence interval. So we would reject the null hypothesis when it's outside of that. So the p-value is low compared to an alpha of 0.10. That's low. It's in the rejection zone here. So we can see all three methods tell us that we need to reject the null hypothesis. There is enough evidence to support the company's claim, which was our alternative, that the standard deviation is less than 1.4 minutes.